Here we are in section 7-2, exercises 1 through 6. We're supposed to simplify each expression. Here we have the square root of 50. Now in each of these, you'll notice that they don't come out perfectly, but our job is to simplify them so that they, as much as can be simplified, is. And if we're talking the square root world, then we need to worry about the perfect squares. So let's talk about the perfect squares. That's 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, and so forth. 81, 100, 121, 144. So these are the perfect squares, and if there are more here, and you can actually tell when these show up. If you can't see it all right at the beginning, you can use your prime factorization. But here we're like, do any of these numbers go into 50? And we're like, yes, there's a 25 right there. So we can rewrite this as the square root of 25 times 2. And the square root of 25, we do know that one. That's unsimplified. Square root of 25 is 5. So we get 5 square roots of 2. And square root of 2 doesn't have anything that goes into it. And yes, there we go. I'm going to do this one other way just to make sure we understand. If we did 50 and we broke it down, and you did say 10 times 5 and then 5 times 2, that'd be the square root of 5 times 5 times 2. A pair of numbers in the prime factorization indicate that there is a perfect square because 5 times 5 is a perfect square. And you'll notice that when it escapes, square root of 5 times 5 is just a 5. So any pair, any perfect square under the square root get to escape back into the rational world, and the square root of 2 stays irrational. All right, let's move on to the next one. Square root of 27. So we look at this and we're like, oh, do any of those go into it? Yes, this is the square root of 9 times 3. And the square root of 9 is indeed 3. And that square root of 3 stays right there, irrational. So the square root of 9 is 3 times the square root of 3. And again, prime factorization, it would have looked like this. 27 breaks up into a 9 and a 3, which breaks up into a 3 and a 3. So we had the square root of 3 times 3 times 3. And any set of 2 get to escape. And look at that. Just like that. Good deal. All right, let's try the next one. Number 3, square root of 48. Yeah, what goes into this one? A 4 goes into it, but a 12 goes into it. Let's go ahead and use that prime factorization method and see how that works. 48 goes into 4 times 12, which is 4 times 3, which is 2 times 2. And nope, 3 doesn't go down any further. That 4 does go down into 2 times 2. So this is really the square root of 2 times 2 times 2 times 2 times 3. So this set come out as a 2. This set comes out as a 2. And then that 3 has to stay in the square root. So this is now 4 square roots of 3 is the correct thing. And yeah, we could have done that at the very beginning. If you notice, 16 times 3 would have given us 48. So square root of 16 is 4 square roots of 3. All right, let's do that next one. Ooh, see, in this one, I don't know exactly right here which one of these goes into it right away. So I'm going to have to do that prime factorization. 384. Good thing we practiced that. 2, and it looks like 192. 2 and 96. 2 and 48. Is that correct? And then, let me see. Oh, yeah. And then we did 48 up there. So we've got 4 and 12. That goes 2 and 2, 2 and 6, 2 and 3. Okay, so let's write all this out. Square root of 384 is actually 1, 2, 3, 4, 5, 6, 7 2's. 2 times 2 times 2 times 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 2. That's 5, 6, 7, and then a 3. So let's see what happens. This set, square root of 2 times 2 is just a 2. That set comes out as another 2, a real rational 2. Square root of that 4 is another one. And then we get 2 times 3 in here. So that is 2 times 2 is 8 times square root of 6. 8 square roots of 6, which is fascinating. Now I know what I could have done here. It turns out that this is 64 times 6. Wow, look at that. I didn't even know that was going to happen. And so, yeah, sometimes it takes a little work. All right, number 5. As we look at number 5 here, this is the cube root of 24. Now, we're dealing in the cube root world, so we need perfect cubes. Oh boy, do you remember those? Perfect cubes are 1 times 1 times 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343. 8 cubed is 512, 9 cubed is 729, and then 10 cubed is 1,000. So we need one of these numbers to go in. And yeah, there it is right there, 8. This is going to be the cube root of 8 times 3. And we know what the cube root of 8 is. That's 2. Just the normal 2, cube root of 3. So let's see how this works with prime factorization. If you were to break down 24, 6 times 4, that's a 2 times a 3 and a 2 times a 2. So this is the cube root of 2 times 2 times 2 times 3. So there's its genetic code. It's prime factorization right there. And now cube root undoes a perfect cube. So a set of 3. When you find a set of 3 under a cube root, that's what cube root of 2 times 2 times 2 is 2. Cube root of 8. And so that's what came out right there. And then cube root of 3 does not come out even and remains the irrational portion of that number. All right, next one. We're going pretty well here. Oh no, 5th root of 486. That means we need to look for perfect fifths. We could write them up and do it this way, or we could prime factorize and look for a set of 5. That's how I know I have a perfect fifth. So this prime factorization is actually pretty powerful. So let's try that. 486. That's 2 and 243. Some of you may remember 243 is a perfect fifth, but if you didn't, let's go ahead and keep doing that. 3 and 81. That's 9 and 9. That's 3 and 3 and 3 and 3. So if we were to write this out, we have the 5th root of, oh, better keep that going, 3 times 3 times 3 times 3 times 3 times 2. So 3 times 3 times 3 times 3 times 3 times 2. And that timesing 5 times in a row right there, that's a set of 5. That's a perfect fifth. So that's going to come out. 5th root of 3 to the 5th is 3. And then that 2 has to stay in there as an irrational number and does not come out nicely. So you could have seen it right here. 5th root of 243 is 3, and then the 5th root of 2 does not come out nice. Excellent.